Okay, good morning, everyone. I guess we can get started on the second last, or probably the last actual computational astrophysics lecture of this program. So this is the last numerical relativity talk as well. In this lecture, I'm going to sort of give an overview of this generalized harmonic evolution. So what I'll be talking about is I'll describe this generalized harmonic decomposition of the Einstein field equations and describe how you use them to solve the field equations. I'll then give an example of a binary black hole merger simulation computed with these generalized harmonic formalism. And then I'll just, a few sort of disconnected related topics. I'll talk about a few sort of bric-a-brac things. And this is sort of you can see that this workshop is winding down, and it was certainly the same way yesterday preparing these lectures. I started losing steam around midnight last night, and I could not. I wanted to talk a bit about BSSN and perhaps give an example of PMR, AMRD, but it just things just came to a halt. So just a few loose topics and then some concluding remarks at the end. Okay, so generalized harmonic decomposition, and perhaps the first thing that might come to mind after all these relativity lectures is, come on, why more formalism? But actually, if you think about the field equations, it's really all the advances that have been made recently has been achieved by understanding the structure of the field equations and developing these new formalisms. It really, to some extent, has not come through advances in computational methods. I mean, if you think of the kind of computational methods that are used in relativity, they've really been around for a while. I mean, I guess many branches of computational science are like that. It's rare that sort of new algorithms are developed, in particularly by the scientists. It's more that the scientists borrow algorithms that computer scientists have developed, and that's been the case with relativity. And so, for example, the bread and butter techniques that all groups use, not just the finite difference-based techniques that I have described, but basically all the techniques are relatively old and well understood. For example, finite difference with adaptive mesh refinement that I described, multigrid or solving elliptic equations, these multi-patch methods, pseudospectral domain decomposition for parallelization, etc. I mean, in some sense, all of these basic techniques work very well with the field equations. There isn't something particular about them that requires unusual numerical algorithms. The other thing that, sort of the other reason why it's mostly been in the formalism, essentially, contemporary computers are powerful enough that we can actually solve the full field equations in certain situations of interest, for example, a binary black hole problem. So I think what you've seen in many of the lectures before is in situations, other astrophysical situations, the physics is incredibly complicated. Like the radiation transport, a 7-dimensional problem to do it properly. I mean, there's some incredibly complicated physics that you just can't solve on contemporary computers without approximating the physics to some extent. The Einstein equations, even though they are somewhat complicated, luckily they're not that complicated. We don't have to sort of approximate the field equations before we can solve them. We can actually solve them exactly where exactly is as small as truncation error as we can throw computer power at. That's a very interesting situation in physics if you think about it a little bit. I mean, gravity is one of the fundamental forces, barring quantum effects. And we're able to solve it exactly in situations, sort of in macroscopic situations. It's just even silly to think of trying to perhaps, use path integrals to compute, radiation fluxes in an accretion disk, for instance. I mean, you don't use fundamental physics in these large-scale astrophysical computations, except for gravity, which is kind of interesting. So in some sense then, the difficulty in solving the field equations has really all been in the formalism. And if, for example, if we had just stopped after the third lecture, I would probably just essentially have been describing the state of the field to you several years ago. So in some sense, so don't be discouraged by this, but this is sort of the real perhaps the most important thing to take away is that the ADM formalism that I gave you before I mean, it's really great to understand some of these things, and we're going to use it today to understand some aspects of generalized harmonic evolution, in particular how you choose gauging generalized harmonic coordinates and the nature of the constraints. But in some sense, the ADM by itself, as I've mentioned several times before, is not a really good general purpose solution procedure, and generalized harmonic is. Again, there is one other method which is based on ADM, BSSN, Baumgart, Shapiro, Shibata, Nakamura. I don't have time to go into it here, but starting from the ADM, it's a relatively simple, at least conceptually, extension of ADM. The thing that I like about generalized harmonic, however, at least in particular in sort of formally describing things, is mathematically it sort of makes sense. You can imagine why it works. I think with BSSN it's still a little bit more, a bit like magic. I don't think anyone really knows why BSSN works as well as it does. I mean, with the generalized harmonic, I think it's on a stronger mathematical basis as to why it works.
Could you tell us just a little bit about the dates? ADM was sort of, 1960s invention?
Right, so I'd probably say like the ADM form that we see here, and particularly for numerical methods, was in the 70s. So with York, so ADM themselves were in the 60s. York was sort of the 70s. Yeah, so I think it had started even before B, S, S, and N. There are several other people that started, playing around with the ADM equations, and over the years, several of them made little sort of changes to it. And I think what is probably referred to as BSSN, although that terminology I think came around in the mid-90s. Perhaps Luis, he might correct me if I get these dates wrong. But and since then, so one of the breakthroughs with BSSN was not really another modification of BSSN, but so there's one sort of a technical detail. So I describe with black hole evolutions, we use excision here with generalized harmonic, and that's a general technique you should be able to use with most equations. They did not, when they used excision, things didn't work with BSSN, and they've got this. There's this technique for specifying initial data called the puncture technique. Essentially, it's like the wormhole throat picture of a Schwarzschild geometry. You've got our space-time. You go through the throat at r equals 2m, and you go into another universe. So if you bring that other universe into a point, from our point of view, it's this little puncture. It's a singularity at the origin. So that was a way of specifying initial data. And one of the things that they did was say, well, let's not excise this. Let's just move this. Let this little puncture move through the grid. And that worked. And I mean, I think, if you think about it, here's it's a singular point. Things are really infinite there. Why? They just discretize right over the puncture. They sort of discretize as if there's nothing there, and it works. And so, I mean, at least at a first glance, it sounds like madness. At the second, when you look at it a little bit more closely, I think one reason why that singularity doesn't destroy things is for it to work, you have to be very careful with the gauge that you choose. And the gauge that they choose, the lapse function goes to 0 sufficiently rapidly as you approach this puncture. So in the evolution equation, sort of the time derivative of things is proportional usually to the lapse times something. So you've got that something which is going to infinity, the lapse is going to 0. And if you do things just right, you can get away with. It seems to work.
Just one follow-up. Your own baby, GH, was your great success, 2005. You wrote in your review article, was tried by Uncle Albert himself back in 1912 or something.
Yes, I'll give you a little bit of an overview of that in the next. Yeah. Okay. So let's talk about harmonic coordinates, and that's essentially the next couple of slides. I'll sort of go into that. So to get to generalized harmonic coordinates, we first have to start with harmonic coordinates. And this is the formal definition of what harmonic coordinates are. So essentially what you do is each one of the 4 space-time coordinates, your x, mu, you demand that it independently satisfies a covariant wave equation. So this is not a vector equation. This is a set of 4 scalar equations, one for each space-time coordinate. So you're saying essentially box x equals 0. And this is just the form of that expanded in terms of the metric. So in some sense that already seems like a very strange condition. What does it mean for the coordinates to satisfy wave equations? And again, in relativity, geometry is so entangled with coordinates that, in some sense, whether is it coordinate or metric, there's not such a clean distinction. So, I mean, you can do things that seem a bit strange like this. The formal reason for why people did this is it sort of fixes the character of the equations, of the Einstein equations in a very nice way. And you can almost think of this sort of the analog in general relativity of the Lorentz gauge in Maxwell's equations. In particular, here in relativity, what it does, so if you take this as your so you impose these as coordinate conditions. You've got 4 coordinate degrees of freedom. You impose these 4 coordinate conditions, and then you take this expression and you manipulate it. So you compute derivatives of this, etc. And you take those results and you plug them into the Einstein equations written in terms of the metric. What this does is it converts the equations into a manifestly hyperbolic form. So then the only second derivative terms that appear in the Einstein equations is this operator here. So here we've got the 10 indices, and we're just essentially taking the wave operator acting on each metric independently. So we've taken the Einstein equations, which didn't have any definite character, and we've converted them into a hyperbolic system of equations. So a wave equation essentially for each of each component of the Einstein tensor. And then the lower order nonlinearities and couplings, etc. I mean, they still remain, but at least the principal parts are now wave equations. Okay, so this is getting back to comments. So I mean, harmonic coordinates are not new in any sense. I mean, they're in some sense even as old as relativity. So Einstein used them back in 1912, or at least they're in his notebooks. There's evidence that he used harmonic coordinates when he was searching for his theory of gravity. At least at the time they were called isothermal and not harmonic. And even since then, I mean, they've really been a sort of an instrumental tool in the formal analysis of the field equations. Going back to some very early work on the characteristic structure, perhaps some of the most important work by Choquet-Bruhat, who showed that these are sort of well-posed equations that given the initial conditions, you can actually show existence and uniqueness of solutions, which is essential for any theory which we expect is relevant in physics. I mean, physicists sometimes are a bit cavalier with their intuition. We think that this has to be right, so it's got to describe nature. Minkowski space has to be stable, for example. But with a theory as complicated as the Einstein equations, it might have just been lucky that this mathematical structure happened to quantify certain aspects of space-time, such as Minkowski space, but the theory might not be well-behaved or well-posed, and so proving that from a mathematical point of view is important. So it's been a very well-known and useful tool to go to harmonic coordinates in analytic relativity, but in numerical relativity, it's essentially been, till recently been ignored, and I think largely because of the misguided belief that these coordinates are prone to developing coordinate singularities. So there was this idea that they would be pathological. I mean, the idea is sort of, just thinking loosely speaking, so we imagine that we're now saying that the coordinates are going to satisfy a wave equation. So it admits wave-like solutions. And imagine on the diagram I showed you, you're slicing space-time. Perhaps the easiest coordinate to think of is the time coordinate. In other words, that's your slicing. Now imagine you've got waves in your slicing. So time is moving forwards, but you superimpose waves on your slicing. And as these waves travel, they can interact, they can interfere, they can be constructive interference. And when sort of two waves interfere, sort of at the peaks of the waves, time is going to move forward faster than it would normally. At the troughs, it's going to go slower. And if the amplitudes of the waves are large enough, when it goes slower, it could actually come to a stop at some point and want to go moving backwards in time. And if things like that happen, you run into a coordinate singularity and the simulation it crashes. It's not going to work. So in some sense, there was this argument that, okay, because these are wave equations, generically this kind of behavior is going to happen. You've got black holes that are stirring up the coordinates. They're going to be emitting gauge waves. You're not going to be able to avoid this. And I should also say, incidentally, the way that harmonic coordinates were used traditionally was within the ADM formalism. So again, in the ADM formalism, you can completely specify your gauge with the lapse and the shift, and you can choose a lapse and the shift such that you get harmonic gauge. However, in some sense, that doesn't fix some of the problems in particular with these constraint violations. So you can do harmonic gauge in ADM, but it's not a good coordinate, it's not a good formulation to evolve the field equations. So I think that, so in some sense this was completely, or harmonic coordinates were avoided because of this belief. And now I think in hindsight, now looking at some of these black hole simulations, harmonic coordinates themselves are fine. So at the time, so it's okay, let's just take that there are these possible problems. In some cases, that is correct. It's not that this is false. There are certainly examples where that happens. But David Garfinkel several years ago noted, well, there's at least an in-principle solution. He was looking at cosmological simulations. And so he noted that in this paper, but he actually never tried the solution. And the potential solution is just generalized harmonic coordinates. And so the idea here, and I guess they were formally studied by Friedrich several years before already, but the idea is, okay, the coordinates satisfy in harmonic a wave equation. Well, let's just add some source functions. So it's not a homogeneous wave equation anymore. We're free to add some arbitrary functions to the right-hand side. In some sense, how this could help is, if you now think of it, if you were clever enough in choosing these source functions, somehow, in some sense, you're not using up your coordinate degrees of freedom anymore. Because any metric can be written in this form with an appropriate choice of h. And to see that, just take your metric in your favorite coordinates. It doesn't have to be harmonic coordinates. It could be any coordinates you want. And just evaluate this expression. If you know the metric, you can evaluate this. And that tells you what source functions you need to put that metric in generalized harmonic form. So at this stage now, we're sort of thinking that we're imposing this as a condition, but we're sort of adding our coordinate degrees of freedom back. And the trick then is, so the same manipulations that were done before, differentiating these things to try to get rid of the terms that destroy the hyperbolicity of the field equations. You do the same things, you plug them into the field equations, you get this system of equations. So this is exactly the same as we had before, except if you substitute h equal to 0, you get harmonic h. You get these extra terms. But the same sort of trick has worked here to fix the character of the principal part of the field equation. So the second derivative terms, it's just this wave operator. And so what you do then is you do this trick, and now at this stage, you consider these to be independent functions. In other words, you forget that they really should satisfy this relationship if you were going to have a solution to the field equations, and you treat them as independent functions. So in other words, and so if you want to solve the system of equations, you now have to specify additional evolution equations for these source functions. So that's the idea behind generalized harmonic coordinates, is we want to have the benefits of harmonic coordinates in making the field equations manifestly hyperbolic, but we don't want to throw away our coordinate degrees of freedom because of this possibility that the coordinates can go bad. So you can imagine if harmonic coordinates h equals 0 is pathological by themselves, but these h's are general enough to describe any space-time. Now, if you can come up with an appropriate source function, you could, at least in principle, avoid those problems with the waves. In practice, it might be more complicated, but in any case, here is at least a mechanism where those problems won't arise. Okay, but now we have this system of equations, but we don't really necessarily care for all of the solutions to the system of equations. We want to satisfy the Einstein equations. In other words, we want solutions where this constraint is satisfied for all time. So, I mean, how do we go about doing that? And so the claim is, if we solve the system of equations, so these 10 equations for the metric, and now we add some four whatever gauge equations for these source functions. And the claim is that if we choose initial conditions, so this is very much like the ADM formalism, if we choose initial conditions where these constraints now, so this is just the previous definition of harmonic coordinates, but I've moved them this to the right-hand side. So for any solution to the Einstein equations, these functions C have to be 0. So if we choose initial conditions in the metric such that C is equal to 0 and such that its first time derivative is 0, and we choose boundary conditions that are consistent with that, then an analytic property of this equations is that the constraints will be satisfied for all time. In some sense, here's the proof of it. You can show just from using geometric identities that the constraints themselves satisfy a wave equation, but it's got the source term. But the source term is proportional to the constraints. So you can see, sort of loosely speaking, you want to specify, if you want C to be 0 for all time, this is the equation that's going to satisfy it. So to achieve that, if it's 0 initially and its first time derivative is 0, C equals 0 is a solution for all time. So at least at the formal mathematical level, just like with the ADM equations, even though we have this larger system of equations, we can guarantee that we just select those subset of solutions that we're interested in by solving the constraints at the initial time. And here the constraints are that the C and C dot is equal to 0. So this is sort of just sort of rehashing a little bit of what I've said. And again, from at least at the first glance, it really looks like we've done magic. We've done stuff that we shouldn't be able to do. I mean, we really, in some sense, we've taken equations that have no definite character. We've added some stuff to it. We've sort of ignored the fact that there are relationships between that stuff. And somehow now we've got a completely general, mathematically well-posed evolution system with all our gauge degrees of freedom intact. And in some sense, but if you think about it, we're not really doing anything magical. In some sense, what you're doing is you're expanding the system of equations in such a particular manner that that expanded system has the mathematical properties that you desire. And then but now that you've got an expanded system, you want to restrict the class of solutions to those that you're interested in. And in this case, the way to restrict the solutions is through appropriate choice of initial conditions. So perhaps you can imagine, solution space to this expanded system is a three-dimensional volume. But solutions that we're interested in is this two-dimensional sort of hypersurface, or just a hill in this three-dimensional space. And so starting with initial conditions, we want a trajectory that follows this hill. Of course, general solutions to this equations, they can do anything. You can, the trajectory can go flying off into space or whatever. So we're now at the stage we've got a mathematically well-posed system, but the really important question still remains, and the same like with the ADM and all these free evolution schemes. We've now expanded the system so that we've got a nice, it's got a nice mathematical character. But because it's an expanded system, even if we can start with initial conditions that exactly satisfy the constraints, how are they going to behave when we evolve the system with these equations? And I think if you think in some sense just about what possibly might happen if we had a system of PDEs. I mean, this is in some sense you think like, how is this any different from just regular truncation error? And the one thing that makes it different generically are these constraints. And if you think, let's just imagine a system of PDEs where there weren't constraints. So every solution is a viable solution. We start with exact initial conditions, and we're going to evolve this forwards in time. So you might think, well, because of truncation error, how fast can that numerical solution deviate from the continuum solution that we're interested in? And I think, now this is definitely not a general property, but I think if you just can imagine, if you're in a region of solution space where there aren't exponential instabilities, so the solutions are relatively well behaved, and you evolve the equations forward one time step in a system without constraints. Well, in some sense, the most error in this trajectory that you can add is going to be proportional to the truncation error times your time step times delta t. But now at that next time step, that's perfectly valid initial conditions for a next time step. And so how much error are you going to accumulate from one time step to the next? Another delta t times the truncation error. So in a system without constraints, generically at some fixed resolution, it's going to be difficult to imagine the constraints would grow faster than linearly with time. On the other hand, if there are constraints, in other words, this larger system of equations is really a subset of solutions that you're interested in, it's perfectly to imagine, well, in taking one time step, how fast or how large can these constraints grow in one time step? And it's certainly conceivable that the amount that it could grow, well, it will be times delta t but it could be proportional to how large the constraints are at that initial time to begin with. And if the rate of change of something is proportional to how much of that something is there, I mean, that's exponential growth. That's the definition of how you get exponential behavior. So these constraint systems, at least it's very natural to expect generically that you're going to have exponential solutions. And so then the important question is, we have this constraint system that we're solving. Does it admit exponential growth of the constraints? And for the generalized harmonic form, yes, unfortunately it does. And not generically, but it turns out that for space-time that contains black holes, it does have exponentially growing constraint-violating modes. And so in some sense, just sort of a bit of a little bit more of the history, sort of back at that time, there was really a cottage industry of inventing new formalisms. And most of them, at least in my opinion, were hideously complicated because of the number of additional variables, etc., that were being introduced. For whatever reasons, reduction to first order, etc. And, essentially every single one of them not only had your 4 fundamental constraints that come from the Einstein equations, but you had a host of additional constraints coming from all the extra little bits and pieces that were added to try to give these equations nice character. And so at least from that point of view, if you think like generically with the free evolution, you have to deal with these constraints in some fashion. And that was like, so if you're going to start with a system, you want to start with a system which has the simplest constraint structure. And at least I don't think there's something that's simpler than harmonic coordinates, at least a hyperbolic, manifestly strongly hyperbolic system that only has the 4 fundamental Einstein constraints. And so you can imagine if it's the simplest structure for this expanded system, it might be the easiest to deal with. And that seems to have been the case now. I'm saying here the cure to this problem, an apparent cure, because there's no proof that it's going to work in general. And it probably won't work in all situations, but at least it does for black holes. And this was suggested by Karsten Gundlach, based on work that he had done with the so-called Z4 formalism. And Z4 looks very similar to harmonic, so he had done stuff with Z4, and that suggested it might work with harmonic. And so the idea is, again, we've got this expanded system of equations, we've got these constraints, we can still play around with the equations by essentially adding any function of the constraints that we want. Right? So here we've got the Einstein equations, and now we're going to add some function of the constraints. Now, a solution to the Einstein equations have c equals 0, so we're adding 0 to the equations, we're not changing them at all. However, by adding these c's, we're changing sort of that manifold when you start evolving away from the surface of solutions to the Einstein equations. And this particular set of functions was chosen so that if you look at the way that the constraints propagate, so again, before we had this sort of this wave equation with this homogeneous source term, you're still adding a bit so it's still homogeneous in the constraints. So the property of a 4, if you start with solutions where c and c dot is equal to 0, you're still going to satisfy the constraints. But now you've added this term. And you can sort of imagine that this sort of looks like a damping term. If you have a wave equation and you add a term that's proportional to the time derivative of the field with an appropriate sign, it's going to act like a damping term. And here the time derivative comes in. We're taking the gradient of this thing with respect to the normal. The normal is our time-like coordinate. So this is sort of a time derivative of the field that we're adding. The thing which messes this up a little bit is this is a symmetrization of that. So we're also taking a gradient of the constraint and dotting it in with the normal. So that's sort of why this is not, it's probably difficult to prove that this is 100% of the time going to act like a damping term. But at least that's the idea. So now we've added this function of the constraints. And incidentally, you want to sort of be careful that you don't affect the hyperbolicity of the equation. So this particular function, again, only contains first derivatives of the metric. So we're not changing the principal part of the metric as long as we don't add gradients of the constraints. So we're keeping this thing hyperbolic, and we're adding things such that it looks like we're adding a damping term. And so Karsten was able to prove that at least if you take Minkowski space with small perturbations that violate the constraints, then this does exponentially damp those violations away. And for black hole space-times, there's no proof that it works, but empirically it does. We just you choose this kappa. So here I've written it as a constant. You can it can be any sort of space-time function you want. So the rule of thumb is, if you have a black hole with mass m, make kappa of order 1 over m, sort of just from dimensional arguments. So if it's too small, it's not going to work. In theory, if it's arbitrarily large, it should still work, but in numerics, you're going to get problem if you take finite time steps. But yeah, so this is sort of the controllable parameter, and the thing is, it doesn't have to be fine-tuned, at least. It's just if it's large enough that it starts working, and it's not too large that you're going to run into problems with very large relative time steps, then it works. Okay, so just to show you, excuse me, one example. So this is an evolution of just a Schwarzschild black hole in axisymmetry. So this is the symmetry axis. Again, this is with mesh refinement with a generalized harmonic form. And what I'm showing here is so just taking the solution and evaluating the constraints. So of course, analytically there's 0. Numerically, it's going to be of order the truncation error. This is a logarithmic scale, and there's no normalization to this. This is just to show the difference with and without constraint damping. So we're taking exactly the same initial conditions, the same generalized harmonic form. Everything is the same except that parameter k is 0 in one case and non-zero in the other. And incidentally, this is a refinement thing, and just for simplicity, I didn't bother evaluating the constraints on the boundaries. I didn't want to take the effort to switch from center to sideways derivatives, but this is not something that propagates. It's an after-the-fact thing, so it's not really an issue. But those black things are just where I didn't evaluate the constraints. So the left is plain generalized harmonic. The right is generalized harmonic with constraint damping. You can see. Okay, you can't see. Thought I'd fix that. Let's see. Okay. Let's try again. I can see just night and day different evolution. The one on the left again was without constraint damping, so you could see that the constraints, there was some non-trivial source of constraints. They were propagating outwards, so they were satisfying that wave equation. And incidentally, like without black holes in the domain, that kind of behavior did happen, but they just propagate away. They would sort of be benign. But with black holes, for some reason, there's an interaction in that strong field regime, and it causes the amplitude to grow. And very soon, the reason why it's black is a simulation crashed. It grew sufficiently large that things nan. But on the right-hand side, you can see there's a little bit of dynamics initially, but it settles down to essentially numerically a static state at late time. So sort of adding these little nutritious zeros to the field equations really has, night and day difference in the simulations at the end of the day. Okay, so now we've got this formalism to generalize harmonic with constraint damping that seems to work. But I mentioned there is this potential problem with gauge. So the question is, well, how do we use this coordinate freedom that we have to choose the gauge? I mean, what do these things represent in some kind of physical geometric fashion? And just by looking at that, the definition, box x is equal to h, I don't think it really gives you too much insight into what these source functions are. And so the thing that you can do to understand sort of what they represent is to go back to the ADM decomposition. So thinking of space-times in terms of a spatial metric h and these coordinate degrees of freedom, the lapse and the shift. And if we do that, we can just write what the definition of harmonic coordinates are in terms of the lapse and the shift. So we take that box x equals h, we take that equation, we contract it with a normal, and we take that equation and do the spatial projection, and we get this relationship. And here this gamma bar is the connection of the spatial metric. So everything, here on the right-hand side are purely spatial objects. So we've sort of done an ADM decomposition of the generalized harmonic condition. And just sort of rewriting things a little bit, these are sort of purely spatial tensors, but sort of the important quantities are these terms. Here we've got gradients of the lapse dotted into the normal vector, so it's essentially a time derivative, and that's sort of written down here. So what it's essentially telling you is sort of the time-like component of this. So the time source function is essentially the time derivative of the lapse. And the spatial source functions are essentially the time derivative of the shift vector. So that's very nice, because in some sense we don't have to redevelop 20, 30 years of research into gauge conditions. And I didn't speak much about coordinate conditions, but there's a lot of work that's been done over the years in figuring out various slicings and coordinate conditions for space-times, thinking in terms of the lapse and the shift. But now, in some sense, what this says is we can inherit all of those ideas by appropriately choosing the source functions, guided by this relationship. So, for example, the idea is that you have some coordinate condition that makes geometric sense to you, for example, a maximal slicing or whatever. So if you know what that coordinate condition is in terms of the lapse and the shift, you should be able to come up with some conditions on the source functions to get to that same gauge. It might not be easy, for example, with elliptic gauges like the maximal slicing, but in general, you should be able to come up at least with sort of driver gauges, because the source functions are proportional to time derivatives. If you know what the lapse and the shift are, you should be able to come up with equations that drive the space to that particular slicing. And so, for example, one class of coordinates that has been useful in evolving black hole space-times. And this is not, I think, a general statement that in black hole space-times you want the lapse to be far from zero. But I just find in my simulations, at least with the code that I was using a while back, when the lapse function got too close to zero, when black holes form, that sort of generically happens. You have gravitational collapse, the lapse sort of represents the redshift, and even in the horizon penetrating coordinate system, generically you have the lapse going close to zero. And that seemed to result in some numerical instabilities in my code. So I just thought, well, let's choose a slice that tries to drive the lapse back to one. So try to get sort of a geodesic type slicing in the lapse. And this is then, there are various ways you can imagine doing it. I thought like just doing a covariant wave operator would be nice from sort of a symmetry point of view. Every equation for the metric and the source functions are wave equations. And this guarantees that we're not messing up the hyperbolicity of the expanded system. But so this is just sort of a driven wave equation where if the lapse isn't one, then these source terms appear and drive the source function such that the corresponding time derivative of the lapse will push it towards one. And then this is just a damping term. In certain situations, when there are strong dynamics, this driving can be a bit too strong and set up oscillations in the lapse. And so this just damps it out. So this is one example. Of course, you don't have to appeal to the lapse and the shift. You can come up, there are other ways of sort of coming up with gauge conditions. I just wanted to mention this one damped harmonic coordinates. And this is just, well, let's sort of take that idea seriously that there really could be problems in harmonic gauge if there are gauge waves and they superimpose and that causes things to go singular. So let's sort of try to devise a condition that will damp out such coordinate waves. And so the idea is, well, let's sort of, instead of having box x equals 0, let's have box x be some damped wave equation. Let's try to add a damping term to that. Of course, the problem is if you try to do something like that, well, what are you damping the coordinates with respect to? For example, the time coordinate, that is time. How do you damp time with respect to itself? I mean, in some sense, it doesn't quite make sense. But the idea, one way you can try to do something like that is let's assume, so the little x's here are our code coordinates. So these are the coordinates. They satisfy, they're going to have these gauge waves. But let's assume that there exists some well-behaved set of harmonic coordinates. So let's assume that these x bar coordinates, that they're some hypothetical slicing of space-time, they exist. And it's relative to those well-behaved coordinates that our coordinates are exhibiting some large amplitude oscillations. So we've chosen bad coordinates. These things are getting very large, and if we slice the space-time according to that, we run into these problems. But let's assume that they are well-behaved coordinates, and we somehow want to evolve our coordinates such that these waves are damped. And so if you see, well, what would that imply then as a sort of, if we want these equations to satisfy a damped wave equation relative to these well-behaved coordinates, this is the condition that you'd get. And if you say, well, what does that imply for the source functions then? So now we're going to be evolving in these coordinates. We want box h box x equals some source functions, it turns out that this is a condition. So you say that now in our code coordinates, if we specify a source function that's proportional, near kappa is now some constant of proportionality, a damping constant. It's proportional to the difference between the two normal vectors. So here n is just the normal vector of the slice in our code coordinates. And this is the normal vector of that hypothetical well-behaved coordinates. And they just related to each other through some coordinate transformation. Now, of course, the thing is we don't know what this hypothetical coordinate is, but now at this stage we can say, well, let's sort of use that as a guideline, and let's sort of just choose some hypothetical normal vector which might have the kind of properties that we want. So for example, one simple choice is we know that if this is just sort of a unit vector pointing in the time direction, or so-called geodesic coordinates, that's going to be a well-behaved slicing, at least if there are no black holes in the space-time. And so for example, if you do that, let this just be a unit vector in the time direction, then you get this set of algebraic conditions for the source functions. So here, the gauge equations aren't necessarily evolution equations. They turn out to be these just algebraic conditions. And again, I'm writing here the lapse alpha, but this is really the lapse as a function of the other metric components. It's just convenient to write it in terms of the lapse, but there really is no lapse in the equations. It's just all the four metric. And I should point out that this very similar idea was recently proposed by Lindblom and Zalagi. Whoops, and I've misspelled his name. And so they propose something, a specific coordinate system, and that's also within this idea of a damped wave thing where they've just chosen a slightly more complicated form for this normal that they want. And so just one example then. So I mentioned in binary black hole simulations, it really we haven't had to use these damped harmonic coordinates. In fact, pure harmonic gauge seems to be perfectly adequate for binary black hole simulations. So if people had been brave enough to just try pure harmonic evolution before, it would have worked with black holes. But like one reason for looking at this damped harmonic gauge was some work I've been doing on looking at high-speed soliton collisions. So this is not perhaps astrophysically relevant, except if there are large extra dimensions. And you've probably heard about the LHC being a black hole factory and all of that stuff and destroying the Earth. Well, at least from my point of view, an interesting question is, well, is that really possible? If you have these really large particle collisions, do black holes actually form? And that's really a classical argument that's been used in the LHC. There's nothing about quantum gravity, so it's purely classical. And so these were some simulations that I did with Matt Choptwick of taking a model of a particle, a soliton, and trying to collide them at very large gamma factors. And what we found was that even at modest gamma factors, when you start with these initial conditions, you boost these solitons. They're going at, in this case, this is gamma equals 4, so relatively large. And you get a very sharp, almost not a shock wave, but it's smooth, but a very rapid change in the slicing. So you get an almost shock wave in the time coordinate that's propagating towards each other. And when they collide, you really do get this problem where the slice goes singular. And so this is just an example to show the difference with this damping and what it really does. So the simulation on the left, this is showing the lapse function for one of these collisions. So this is axisymmetric again. This is where the solitons are. So they're actually spherically symmetric, but these profiles are squished because of the Lorentz boosting. And you might not see it towards the end, but so they're going towards each other. And as they approach, you can see, there you can see things become really nasty in the lapse. In particular, at points, it goes to 0, which means the slice wants to stop and go backwards in time. And at this point, the simulation breaks down. And in particular, the thing is that it broke down before we could detect apparent horizon. So before we could actually answer the question, is a black hole forming or not? And now with the damped harmonic gauge, so this is the case which actually does form a black hole. So we're safe. The LHC is going to form black holes, and they will destroy the Earth. So science is in a good position. So here you'll see. So initially, I'm starting them both in the same gauge. It's both harmonic, but then I'm transitioning to this damped harmonic. But then after a black hole forms, you don't want to use geodesic coordinates. They fall into the black hole. So after a black hole forms, I switch back to harmonic, and then you'll start seeing the typical waves that you would expect. So initially the same, but then it goes to this damped coordinates. You can see it sort of smooths things out a lot. And then at that point, a black hole forms. It switches back to harmonic, and now you can see the sort of dynamics of this black hole settling down to a Schwarzschild black hole. So there are some, perhaps not, well, if there are large extra dimensions, then cosmic rays colliding with the Earth's atmosphere produce black holes. So there might be some astrophysical interest in these things, but at least for astrophysical binaries, it doesn't seem to be. You don't need such damped equations. Okay, one additional comment. So now we've got this formalism where we have shown mathematically that if we want to solve the Einstein equations, we need initial conditions. So again, we have these 10 wave equations for the 10 metric components, second order in time. To give initial conditions, you need the value of the metric and its first time derivative. But there are these relationships that the metric and its first time derivative have to satisfy. In other words, C has to be 0 and C dot has to be 0. So how do we do that in the generalized harmonic formula? And I mean, there are many ways in which you can imagine doing that. But the simplest, again, borrows from ADM technology. And this is, I think, one prescription. And the idea is, well, you just solve the usual ADM constraints in the ADM formalism. So you specify whatever techniques that you do. And again, there are many, in particular the York-Lick-Nurowitz technique is a very sort of formal, general way of solving the constraints. So you solve the initial data in the ADM form. You get your lapse, your shift, your spatial metric, and your gradient of the spatial metric. We need the 4 metric and its time derivative. So if we then choose a source function, again, remember from the definition that these source functions are proportional to the time derivatives of the lapse and shift. So if we choose our initial conditions for the source function, then this condition will give us what the time derivatives of the lapse and the shift are. So now, with this bit of information, we have the time derivatives of the metric and its initial conditions. So we have everything that's necessary to start an evolution. And then the remaining thing to show is just that with this choice, so by construction, C will be 0, but just to show that C dot is 0. And the easiest way to do it is that there's this geometric identity that says that this quantity M, which is just the Einstein residual. So this is the left-hand side minus the right-hand side. So this is 0 for the Einstein equations. So this dotted with a normal vector is equal to this particular function of the constraints. And in particular, remember when we derived the constraints, we just took the Einstein equations and did various projections. So a time-time projection, or M dot n, is just the Hamiltonian constraint, and the spatial projection are just the momentum constraints. So if we've chosen initial conditions that satisfy the ADM constraints, this M vector is 0. So then 0 is equal to this function. If we've chosen conditions that C is 0, then the spatial gradients are going to be 0. And essentially the only non-trivial thing that's left here is the time derivative, C dot n. So if we've chosen things such that M is 0, C is 0 on the initial slice, then this relationship says that C dot will be 0. So in something that's a really nice result, in that we don't have to reinvent ways of specifying consistent initial conditions with generalized harmonic. You just solve the usual ADM constraints, change from alpha, beta, H to G, and evolve. That'll be fine. Okay, so let's do an example of a binary black hole merger. So again, just to remind you, this is a system of equations that I'm going to be solving. So this generalized harmonic, this is actually going to be vacuum, so the stress energy tensor is going to be 0. And for this particular case, I used this wave equation, to keep the lapse not too close to 0 and just spatially harmonic. I'm going to show an example of 2 equal mass, initially non-spinning black holes. And this is a slightly older version of the code that used this one-step Newton-Gauss-Seidel second order. And in principle, this could have been done in RNPL, but it would have been a real nightmare to do all of these equations with excision, etc. So what I did was just put these equations into Maple, substituted in the discrete operators, and asked it to produce Fortran. So in terms of time, this just for references, did several resolutions. The highest resolutions that I'll show you the animation of took about a month of CPU time on 128 nodes. So about a couple of years ago on the Lone Star cluster. And incidentally, that was a really painful cluster to run on because they had this 1 day, I don't know, they might still have that, like a 1 day time limit. So I mean, I knew this was going to take a month, but you can't ask for a month, so you ask for a day, you checkpoint frequently. After a day, you lose your job, then you have to resubmit to the queue. It sometimes sits there for a half a day, sometimes a day it runs again. And at the end, finally, after a couple of months of doing this, your data is distributed into like 30 little bins all over the place. It was a real pain, but things are better today. Incidentally, if you're skeptical, this doesn't look too complicated. Remember, we've got the summation convention here. We are summing over things, and we do have 10 different equations. So here is just sort of a snapshot of the inner loop of the code. Right, so this is the code that Maple produces. And so essentially, at every single grid point, every iteration, every time step, we have to evaluate all of these, sort of essentially about 60 pages of algebra to do one iteration of the field equation. So this, expanding out these things, it does become very messy. And that's why it's a computationally challenging problem. Just there's so many algebraic operations you have to do at each grid point. The method is simple, but it's just a lot of stuff that you have to do. Okay, so I'll show two movies. One of the lapse function, because it's a nice visualization of the space-time. So again, the lapse isn't here it's not a fundamental variable. It's sort of an after-the-fact reconstruction. So this is through the orbital plane. Again, the lapse sort of shows the rate at which a clock's going to flow from an observer that's moving normal to the hypersurface relative to someone at infinity. So sort of a redshift as you approach the black holes. These are non-spinning black holes. So initially the spin is 0, but when they merge, they're going to form a spinning black hole with a spin parameter of 0.7. And about 4% of the rest mass energy is emitted in gravitational waves. So you can see sort of orbiting each other. But as they're orbiting, they're emitting gravitational waves, so they're going to spiral in. It's going to get tighter, and eventually they're going to plunge together to form a spinning black hole, and it's going to ring down to a Kerr black hole. Incidentally, in relativity, there's no intrinsic scale in the field equations. So you can do one simulation for a given mass ratio and scale it to any particular mass. So for example, in this case, if this was supposed to be sort of a real-time representation of this, it would correspond to about 5,000 solar mass black holes. And that's why any relativity talk, if you show things, that the units are usually rescaled in terms of this mass, and then you can just pick a mass for whatever physical time that you want.
So this is the function you use the elliptic solver for, is that right?
So in this case, I don't use that elliptic gauge. That will be with maximal slicing. In the previous example that I showed, this function was solved using an elliptic equation. But this is now, in fact, so this function now is not evolved in the formalism. It's just the four-dimensional metric. But
I thought you said on the previous slide.
Right, so I use
One step, move the Gauss-Seidel to solve the equation above.
Yeah, but that.
It's elliptic to me.
This is the four-dimensional covariant derivative. So this is the D'Alembert operator acting on the source function. And here this alpha is just acting as a source term. And in fact, this is not a variable that's stored in the code. This is a function of the metric. In fact, it's minus 1 over the g upper t squared square root. So I'm just writing it here for simplicity, but this really isn't, it's not actually being evolved. So in the previous example that I showed a couple of days ago with maximal slicing, there alpha is a fundamental variable that you essentially evolve. And for maximal slicing, that does satisfy an elliptic equation. But here there are no elliptic equations. It's a purely hyperbolic system. And this is h sub t, which is actually the variable that's being evolved. Okay. Okay, so the gravitational waves. So now this is the same animation, but zooming out a little bit. So there are the two black holes. Excuse me. An easy way to sort of measure gravitational waves in these simulations is to use a so-called Newman-Penrose scalar. And close to the black holes it's some contraction of the Weyl tensor with an appropriate tetrad. And near the black holes, it doesn't really have any particular meaning as gravitational waves. It's really only far from the black holes that it's a complex quantity. The real and the imaginary components correspond to the plus and the cross polarizations, or at least the second time derivatives of those polarizations. So the structure here, I mean, it's real, but though it doesn't, it's, as I mentioned before, like in the strong field regime, it's difficult to interpret this as anything, in particular, the kind of gravitational waves that, say, LIGO might see. So we've zoomed out because it's sort of in this region that's sufficiently far from the black holes that when the waves propagate out, these become what we can call gravitational waves. So there'll be a couple of things that you know. I'll play this a couple of times. The first thing is that there is so-called junk radiation in the initial data. You'll see this burst of radiation coming out, and that's purely an artifact of the initial data. And the one sort of nice thing that sort of came for free in these simulations is, I mean, before people were able to do the simulation, there was a lot of debate about how significant, because people knew that there was something wrong. The initial data couldn't be exactly right. It's conformally flat. There was no gravitational waves in the initial data. And there was some debate about how significant that might be, and it turns out to be almost nothing. It just, there is something that's wrong, but it propagates away in essentially one light crossing time, so a fraction of an orbit. And then towards the end of the simulation, so this is on a logarithmic scale, you'll see sort of noise, and that's coming from mostly refinement boundary stuff. But so yeah, that burst of radiation, that's junk. It's real, but it's not astrophysical. But now the binaries are orbiting, and these sort of huge lobes, this is the actual gravitational wave emission that's being produced by the motion of the binaries. As they spiral in, the amplitude gets larger, the wavelength gets shorter, so the frequency gets higher, and eventually it merges. It forms this very highly distorted Kerr black hole, and then it quickly rings down to a Kerr black hole. So, for example, this pattern here is largely just noise from refinement boundaries. And then this here is just sitting here at one point, taking this measurement and integrating twice in time. And this is what you usually would see as a gravitational wave signal from this binary, what you would usually call the gravitational wave signal. And this is the kind of thing that LIGO is hopefully trying to, or will be looking at. So what I'm showing here is this psi 4. And to go from psi 4 to this, so I measured this at one point. So this is psi 4 over the domain. But to get this h, you have to integrate that twice in time. Or if you take this and differentiate it twice, then you will get that. But it's just that it's much easier. At least you compute this slice by slice. There are other ways in which you can try to extract that, but this is sort of an easy thing because it's just something that you compute locally. And then after you've got that, if you integrate it with time, you can get the distortion in the metric. So this h is sort of far from the black hole. You've got Minkowski plus this perturbation, and this is this perturbation h. Yeah. Right, so it's got the usual, the quadrupolar antenna pattern. So this, let's see, H plus, oh, right. Right, so actually, so this H plus, I've actually measured it on the North Pole. So that it's actually now coming out some distance, and this is the twice integrated signal on that axis. So yeah, so on the plane, the imaginary component is 0 in this case by symmetry. So this is just the real component, so one of the polarizations. And then normal to the axis, you get both polarizations. And they look very similar. If you looked at any point, you're going to see the same kind of structure. And here I've just shown at that point on the axis what it looks like. So. Yeah, so if you can imagine that, let's say you had a real binary that started from very, very far away. It's slowly spiraling in. And at the point where it's at the same separation as this simulation, in some sense, that's what you'd want to start with as your initial conditions. And so if you think of what that slice is, well, it's going to have the two black holes there, but it's going to have this outgoing wave train of gravitational waves in it already. So if you want to sort of astrophysically relevant initial conditions, you would have to put in that. You'd have to put in the gravitational waves as well. So you know, in some sense, the initial conditions in GR is not just 2-point particles with their velocities. It's, you know, the full space time at that slice. So you want all the gravitational wave degrees of freedom. But there's no, I mean, there are proposals on how you might do that. Say use post-Newtonian theory to say what an approximation for this initial gravitational wave content is. But none of those methods have really been carried out to the point where they're useful or have been tried yet. And so what people do instead is saying, well, let's just say we take two black holes, but the spatial metric doesn't have any gravitational waves in it. It's just conformally flat. So it's this conformal factor times a flat spatial metric. And I sort of misspoke a bit. It's not that it doesn't have any gravitational waves in. We don't put anything in specific. So this conformal flatness assumption does put in some gravitational wave content. It's not the correct one. But luckily, it's not that it's some huge, massive perturbation that's going to sort of fall into the black hole and perturb things. It's sort of this localized blip that propagates outwards, and eventually it sort of leaves behind sort of a clean binary, and then the binary motion starts producing the gravitational waves. Okay, okay, so when I show these things, I always just like to put in some numbers, just for fun. So I'll do that here. So again, we can scale this thing to any mass we want. And so let's just pick something which LIGO might see. So LIGO is going to be sensitive to signals in approaching the kilohertz frequencies. So if we took that simulation, say let's scale it to 210 solar mass black holes. The radius of each black hole then is about 30 kilometers. The radius of the final black hole is about 1,600 kilometers. And the place where I measured this wave on the axis, so if we said this is a sort of a distortion in the metric that's of order 10, 20%, so it's quite a large distortion. But that was at a distance of about 1,500 kilometers from the black hole. In that case, the real-time signal, the frequency of the waves would be in the hundreds of hertz range. And actually, I don't think you'll hear anything, so I'm not going to try, because again, last night things were a bit hectic and I didn't copy all the files over. But essentially, you can actually listen to that signal in audio, and it's this characteristic sort of chirp signal. But if you want to think like, what do these gravitational waves represent? Well, no, they're oscillatory distortions in space-time. And at that distance, the fractional change in length that you'll get if you were standing there is about 3 times 10 to the minus 3. So if you're about 2 meters tall, you go stand there, you get stretched by about 6 millimeters by this gravitational wave as it passes. It's significant. You'll probably feel it, but it's not that large. I mean, if you put LIGO there, like LIGO is 4 kilometers long, it's going to be stretched by about 12 meters, so that's huge. Because LIGO uses very sophisticated laser interferometry to try to measure the changes in the distance. And if you think, well, why does it need to do that? Well, if we think of what this 12 meter change is going to look like by the time it gets to Earth, like let's imagine that this thing went off like near the Virgo cluster, so at a distance of 10 megaparsecs. The amplitude in the metric perturbation decays like 1 over the distance. So what was a 12 meter distortion by the time it gets here is going to be 5 times 10 to the minus 17 meters. Essentially 1/20 of the radius of the proton. So for LIGO to be able to see this, it's got to measure changes in distances over 4 kilometers that are 1/20th the radius of a proton. It seems completely ridiculous and absurd that they decided that they were going to build an experiment to do that. In fact, they can actually get sensitivities much, much less than this. So this is just at the peak of the amplitude. But the astonishing thing is that initial LIGO is at this sensitivity. If an event like this did happen in this last science run in Virgo, it would have seen it clearly. But the other thing that's kind of amazing about not just the instrument, but this is the nature of gravitational waves. So this is a very, very small distortion in space-time in some sense, even close to the black hole. Yet it's carrying a tremendous amount of energy. Like I mentioned, in just those last few cycles and merger, it emits about 4% of its rest mass energy in gravitational waves. So in total, we had 20 solar masses of energy there. So essentially, one solar mass, E equals mc squared, was converted in a few milliseconds into gravitational waves. It's a huge amount of energy, and yet the distortion in space-time is so small. So it's like space-time is very, very stiff. It doesn't want to be distorted. You have to put a lot of energy in to actually get any kind of distortions, which is why we can't build gravitational wave emitters and detectors on Earth. It's just not a feasible endeavor. And so, of course, given how much energy is being emitted, the luminosity is huge. It sort of reaches 10 to the 57 ergs per second for that fraction of the period. Of course, so at that moment when a black hole merger occurs, it's by many orders of magnitude the brightest event in the universe. And another interesting little calculation, this is a very small distortion, but how much energy density is there? And if you could actually take the gravitational waves by the time it reached Earth and converted it into sound waves, it would actually be at 80 decibels. So it would be still carrying a lot of energy. Well, of course, it's not dissipating the energy, but it's still, in some sense, it's carrying macroscopic energy by the time it reaches Earth. Okay, getting back again to the numerics a little bit. So here's just an example again of the adaptive mesh refinement. So in this case, it's not as an extreme example as what was necessary for critical phenomena, but here it's dynamical, and again, it's not something which, like with the critical phenomena, at some point it gets to a point where you can't refine anymore. So in this case, I think it was a total of 8 levels of refinement. So this is the entire computational domain. This is again at one particular time, the lapse function. So I'll just zoom in on one of the black holes, so just going in. And eventually this is the finest mesh and the black hole. And incidentally, I'll say a little bit more about this on one slide. But this is the X-sized region, but this isn't the black hole. The X-sized region is always a little bit inside the black hole and technically inside the apparent horizon. In this case, it's about the actual apparent horizon was something like there, about 50%. This is about a 50% shrunk version of the apparent horizon.
The X-sized region is entirely symmetric,
No, so this is because the other black hole is there. If this were a single black hole, it should be, but now it's being distorted by the other black hole. Right, so zooming outwards. Here you can see it because the color scale, I adjusted the color scale so you could see the structure far away from the black holes, but it is that they are sort of tidally distorting each other. Some of it is coordinate and some of it is real, but so some of it is geometric, some is coordinate, but it actually is a real effect in the domain. It's sort of a bit of trial and error. So the couple of criteria, you don't want it to be too small, because as you approach the true singularity, the gradients are going to get very big, and that could be problematic. So in some sense, you want it sufficiently large that you're far from the singularity, but you don't want it to be too close to the apparent horizon. I'll mention a little bit more about it. But so the way in which you track this black hole is you find the apparent horizon. You don't want to. You could probably do it at every time step, but you don't want to do it exactly at every time step. So at some time step you find the apparent horizon, you shrink it down by some distance, and there's the black hole. Then you keep that X-sized surface fixed, but the actual black hole is going to be moving. So the next time you find the apparent horizon, it's going to be shifted by a little bit, and you want to make sure that it couldn't have possibly moved by enough time from one moment where you find the apparent horizon to the next, that it moved outside the excision surface. Sorry, that was a discombobulated explanation, but essentially it's just that you're not searching for apparent horizons at every single time step. So you want enough of a buffer zone between the horizon and the excision surface that it can't move outside. So in some ways you can think that the black hole is going to be moving, but the excision surface is staying fixed, and you don't want the excision surface to move outside the event horizon. So it's those two things that sort of balance how large the buffer zone is that you want to put. Okay, so now again, sort of a couple of these last minute things that I just threw together. But I think like some of these are important. For instance, this, going back here, so this is the computational domain, and this boundary is actually at spatial infinity. And I mentioned before that in general, if you're placing boundary conditions at some finite difference in a Cauchy code in relativity, it's really problematic what the boundary conditions are, or at least what boundary conditions are. So coming up with mathematically consistent boundary conditions are easy. You can always use Dirichlet or some radiation condition, but boundary conditions that are consistent with the constraints is not easy to come up with. So one, in my opinion, very simple and straightforward solution to the problem is, well, just go to a place where you exactly know what the boundary conditions are, and that's spatial infinity. We know that the metric there, in this case, should be exactly Minkowski. And because in GR, we know that we have to deal with non-trivial coordinates to begin with, even if our mesh is regular, at least in terms of the metric, we might as well exploit that, the coordinate freedom we have. And so that's what this compactification is about. So we choose a coordinate system. So this is now independent of the other slicing gauge conditions we want. So we've got some particular coordinates. Then we do this additional coordinate transformation where we bring spatial infinity to a finite location on the grid. In particular, in this case, I independently compactify the 3 Cartesian-like coordinates. So the code coordinates are the x, y, z. They run from -1 to 1. But the actual sort of physical coordinates are these barred coordinates. And so you can see from, if x goes from -1 to 1, x bar is going from infinity to infinity. So in that case, the spatial grid is actually, the boundary of the computational domain actually is infinity, and we can place Minkowski's the correct boundary conditions there. There's really no problem in figuring out what those are. I guess the possible problems with doing compactification, and put problems in quotes because in practice it's not really a problem, is of course now you've sort of brought all of infinity into a finite region of the grid. As you go far towards the boundary, resolution is going to be, for any finite resolution, how you're going to be able to resolve physical length scales is going to become very, very bad. In particular, effectively, as waves move outwards, they get blue shifted and they slow down because they never reach the boundary. So the problem is at some point they're being blue shifted. With any finite resolution, at some point they'll become sub-mesh scale. And that could be a problem because we know from all the lectures before that, when you start to have features, in particular, which should be smooth, that are not adequately resolved, truncation error dominates. The solution is garbage. So in that case, the way you can sort of solve that problem is just with dissipation. So once it gets blue shifted to a point where the wavelength is small, just smooth it away. And again, here, because the goal is we don't want to actually, we're not really, at some point it would be interesting to get the waves at infinity, but here this is just a mechanism to place well-posed boundary conditions. So we're not interested in resolving the waves after some point, and so we can just get rid of them. So dissipation sort of solves that problem. And just now to show an example, so this is now, again, a black hole merger, but here I've used sort of scalar field collapse to generate the initial conditions. So taking 2 scalar field pulses, very, very dense, that very quickly collapse to form black holes, and I give them some relative boost. So the scalar field pulses collapse to form black holes, and then the black holes merge. But there's some remnant scalar field energy here, and that propagates away. And this is then just to show how wave propagation works in these compactified coordinates. So this is, again, through the orbital plane. The magnitude and the color is sort of the amplitude of the scalar field. So here on the left side is just in the code coordinates. Okay, that was another hiccup that I had. I was editing the stuff, but I didn't transfer it over. So excuse me for a second while I find those animations. Okay, so let's just play it here. So this is that. So you can see there are 2 little black holes, they spiral in, but those are the sort of scalar waves that escape from the system. They're sort of dynamically insignificant after a while, but they propagate outwards. And sort of let me play it again. You can see, one artifact is that because I'm independently compactifying the Cartesian coordinates, a spherical wave becomes square, but that's just a coordinate effect. But more relevant is you can see that it's getting blue shifted, and it's also evolving into coarser regions of the computational domain. So these waves aren't the physical solution, is that the waves they don't decay, they shouldn't vanish, but it's the dissipation that's killing them. And in some sense, what we're saying is at this point, when the waves get there, we really don't care about them. We just don't want.
Where do you extract your waveforms?
So that would be in a regime that's probably around there. So typically, because this isn't a technique to extract the waveforms at a large distance, you want to choose a scale. So say you feel that you have to extract your waves at say 100 m or 200 m, then you'll have to adjust things so that, you have to add resolution so that the waves are still well resolved when they cross that region. But yeah, so with the waveforms that I showed you, that was in a regime. I think that one was actually at 50 m from the source, the previous example that I showed, which is, it's not perhaps as far as one would like, but it's.
Use AMR to track the waves.
Because they volume filling with it. So this is just one burst of waves, but with the waves from the binary, they fill the volume. So you could use AMR, but it would very quickly become a very expensive calculation.
They don't seem to fill the line.
So, because this is just one burst. But so, for example, so yeah, I don't have an example of the uncompactified gravitational waves. But remember, with the gravitational waves, now they were started. This is just also an example with one orbit, but that had 4 orbits, so it was continually producing gravitational waves. Let me go back to the PowerPoint. See, let's go back to this one. Right, so in this example, so what I showed you in this latest animation is essentially just a couple of cycles. But here you've got this entire wave train. Now this is sampled at a point, but this is now going to be spread out over the volume. And in terms of units, the speed of light is 1 year. So this wave train is going to occupy a radius of about 500 m. So this is about 50 m. So this wave train is actually going to occupy a volume that's 10 times larger than what I'm showing you here. So, and that is so essentially volume filling. I mean, the simulation was only run for about this long. So by the end of the simulation, the entire sort of causal future of that initial binary will have to be resolved. And that will be incredibly expensive with AMR. But I guess let's say that is a good point. I mean, sometimes if you want to do, you could resolve them. It's just an issue of computational resources. Oh, let me just then show you the animation. So of that same thing, but transformed to the regular physical coordinates. Right, and there you can see it's more like these spherical waves going out. And and I lost a few animations there, but this is sort of the same view as the gravitational waves of the previous one. So you can see that in real coordinates, you don't get these distortions. And even if I had made the zoom further out, you would still see, I mean, the waves would get, they would lose amplitude because of the dissipation as well. Okay. Yeah.
How do you match the excisions when you measure black hole? Because
Sorry, say again. Can you?
So when do you decide to match the excisions when you measure?
Oh, when they merge. So okay, so I'll actually show you a little animation of the of the apparent horizons. So again, the thing that I'm showing you is when we look for where to excise, we don't find black holes. We don't look for event horizons. I mean, the mathematical definition of an event horizon is the boundary of the causal past or future null infinity. So to really find the event horizon, you'd need to know the entire evolution of the space-time. So the way in the simulation, you could find an approximation to the event horizon by evolving to some point and then like tracing backwards in time to finding the event horizon. But what is practical is to find this apparent horizon. And so one thing with an event horizon, with the black holes, you've probably seen that pair of pants type picture. The black holes, the event horizons, they might be twisting around, but it's essentially a continuous surface that then touches and then joins, and you get the single event horizon that moves together. The apparent horizons, almost for most of the evolution, map on exactly to the event horizons, except near the merger. And then what happens there, and that's sort of luckily for this kind of excision strategy, so you've got these two separate apparent horizons. At the point where sort of near where the black holes merges, you'll get a larger apparent horizon that suddenly pops into existence, that suddenly surrounds these two inner apparent horizons. And so to find the point where we can merge that, I follow the two individual horizons, but keep looking for this third horizon that's going to pop in. So at the point where you sort of transition from this 2 to 1 shape, there are actually three of these horizons present, these apparent horizons. And at that point, then we say, okay, now we found the bigger horizon. We don't have to keep tracking these two small horizons, because it would be technologically kind of challenging to follow these excised regions that go through this topology change. And luckily, this property of apparent horizons is that they don't do that. And that's sort of what I wanted to say on this one semi-final slide. And that's just a comment that about what the nature of the solution is. Remember, we think we're solving for black holes, and we've got gravitational waves, and all of these other interesting things. But those really aren't what the direct solution is giving us. The direct solution is just giving us a metric distributed on a grid. All these things that we identify as gravitational waves and black holes or apparent horizons, we sort of have to extract after the fact. We don't really have these separate objects. And so then this one example was, okay, well, how do we then know that there's a black hole? How can we follow it? We need to know where it is for excision, and it's this apparent horizon idea. And just in case I didn't mention this, the apparent horizon is just what's called a marginally outer trapped surface. So it's if you imagine you've got the surface, and everywhere on the surface you start shining light bulbs or flashlights outwards. Usually, the wavefront is going to expand. But if you have a trapped surface, you shine the light outward and it's just going to hover there. It's not going to go anywhere. And that's because of the structure of space-time. And if you're just inside the trap, this apparent horizon, you shine the light outwards and it's going to contract. And so if you look for that surface where these photons are marginally, just momentarily trapped, that's the definition of the apparent horizon. And you can show mathematically, if cosmic censorship holds, so if there are no naked singularities, that's always inside the event horizon. So that the trapped surface will never be outside the event horizon. And so that's a good sort of local indicator that you can use for the horizon. So here's an example from another merger which shows these apparent horizons, and you'll show how it's sort of Right, so initially there's a little bit of wobbling, and that's purely a coordinate effect. So initially they're very close to the event horizon, so the area always increases. You see some distortion, and then this large, initially distorted apparent horizon sort of is found outside of both of them. And that's where that sort of discontinuous jump is. So if you did look at the event horizon, again, the event horizon would be a continuous surface. It's not necessarily smooth where they merge, but it's continuous. Okay, since we're out of time, let me just conclude. So just following some of the other speakers, let me just sort of give you sort of my sort of biased and humble opinions of, okay, what the future of numerical relativity is. And I think, from my perspective, it's a very bright future. And I think if you just from a theoretical point of view, there's so much about the field equations that we don't know because we haven't been able to find solutions. And now that we finally are able to find solutions, there's really a tremendous amount about gravity could be learned. So that's exciting. On the other hand, I think in a practical sense, the future is still bright and exciting, but it's really all tied to gravitational wave astronomy. And in particular, in terms of being funded for your work, if you want to do work that I think is going to be funded, it's got to be related to gravitational wave astronomy. And in that respect, again, I think the future looks very, very promising. LIGO has reached design sensitivity, and perhaps from that example, you can appreciate what an amazing feat that is, that it can actually measure fractional distances of the order of a fraction of an atomic nucleus over 4 kilometers. So they've actually reached design sensitivity, and advanced LIGO is funded, so it's going to happen. And there's, I think, good expectation that advanced LIGO will actually be able to do some interesting, will make detections and do some interesting science. So in that case, well, what role will numerical relativity still play? And so I think there are a couple of aspects here. So I would say that in principle, the vacuum problem, so binary black holes, sort of at least in that sense has been solved. In the sense, at least the aspects of the problem that we could expect numerics to treat. For example, it's unreasonable given today's computers that we might be able to do extreme mass ratios, 1,000 to 1, with numerical methods. That will just take too long. Or for example, producing full gravitational wave signals for LIGO, which might require perhaps several thousand orbits. Again, that's computationally too expensive. So at least the subset of the problem where we where you'd need a dozen orbits, and then you match that to various analytic estimates of the orbit before and after merger. I think that's, in some sense, that's sort of a solved problem. Though there may still be certain situations where there are sort of surprises. I think if you have near extremal mergers, so black holes that are very close to the Kerr limit, there could be still some interesting things left over. And if there's non-negligible eccentricity before the black holes merge. And the high speed problem. So if the LHC does create black holes, then this is still going to be interesting. However, I think that the more interesting aspect of research in the future is if you include matter. So strong field gravity and matter interactions. And of course, if you want to understand all the details of how to do matter with GR, just attend this workshop, which you have. In particular, this, for example, looking at things like binary neutron stars, neutron star black holes, etc. So that, in some sense, that is the frontier where numerical relativity could still be relevant and interesting, and where advances could be made. I just want to comment a little bit then on sort of my impression of gravitational wave detection. I would say that sometimes gravitational wave detection is sold as it's going to open up this new window to the universe. And if history is a guide, whenever a new part of the electromagnetic spectrum was opened up, great and unexpected things were discovered. And in some sense, that's a little bit disingenuous, in particular with advanced LIGO. And it can't happen because the gravitational waves are so weak when they reach the detectors. You have to do this match filtering type of technique. You have to know what you're going to see to extract it from the signal. So if there's really something new and bizarre out there that we haven't thought about, LIGO might get hints of it. There might be these excess power detections, but it's not going to be able to actually see it. So it's very difficult to see how advanced LIGO could make a profound and fundamental discovery of that sense. However, what I think is reasonable and certainly I think probably more likely than not, so in my sense, sort of the best scenario would be if LIGO does detect things, but there are some discrepancies or some inconsistencies. For example, there's an excess power is detected. There is a consistent set of excess power events detected in a certain range of the frequency spectrum. Perhaps even better, that they are identified that they are electromagnetic counterparts, but no signals actually quite match those events. That would be very interesting. Or, for example, if a detection was made, but it didn't quite fit all the predictions. For example, with binary inspirals, you can imagine trying to search for the whole thing at one go. But there are also these burst searches in LIGO that look for these little bursts of gravitational waves. And for example, you saw in animation, when the black holes merge, they emit this huge burst of quasi-normal ring-down modes. So if a black hole merger occurs nearby, the in-spiral group should detect it, and the burst group should detect it, and the parameters should be consistent. The parameters that show you've got a black hole merging with a certain mass that's going to form a final Kerr black hole. It's the nature of that Kerr black hole that's going to determine the ring down. They should be consistent. Well, what if general relativity isn't quite right? What if things are different in the strong field regime? What if there's something else happening there that we haven't anticipated? But it's not so different that LIGO doesn't miss it completely. Then you might get little things like mismatches between those parameters. And I think, perhaps the history sort of on our side as well, in the sense is that, when we do theory, we often oversimplify things, and nature is often more complicated and interesting. And so I think the best scenario would be nature is more complicated and interesting, but not so much that LIGO misses it, but just enough so that it can give us some hints as what to explore at next. And I think that will then really be a golden age for not just numerical relativity, because as I mentioned, it's going to have to be GR with matter, but sort of computational modeling driven by gravitational wave detection, because then there's going to be this interplay between theory and experiment. And again, if you look at history as your guide, some of the most exciting advances in physics, quantum mechanics, etc., has been made when there have been this interplay between experiment and theory. So, in my opinion, I think the next, at least 5 years before now LIGO sees nothing, that will be exciting. But I think advanced LIGO is going to see something. I think it's going to be exciting. So there's several decades of really interesting research ahead in this field. So thank you all for attending and being warriors. You're out to the end, the last day on Friday. I know it's getting, it's been a tough 2 weeks, so thank you all.